Good evening, everyone, for taking the time to come to this presentation. So, in this hall, we had earlier about presentation about NVMe over fiber channel and previously some file systems and things like that. So, this is a little different topic that we are going to see today. It's machine intelligence in data center networks. So, basically, we have these data centers that are coming up, everywhere, and there are a lot of characteristics of the data that we are getting today from a variety of devices like mobile phones and servers and PCs and all sorts of handheld devices, and everything we take pictures everywhere, we take videos everywhere and upload, and then every time it goes and it just sits in a data center in some storage device and things like that. So as the capacity or the traffic volume to the data center that is growing high, and then the data centers constantly are evolving to kind of adapt and evolve to match the performance expectations and the service level agreements that are put in place for the data centers. So here I'm going to talk some of these aspects of that. So how like the data center networks service level agreements management, and I'm also going to talk about some application workloads that are kind of driving up the data center networks, and then lastly we'll go into these machine intelligence methods that we can employ, and what are some of the use cases for those machine learning intelligence methods. So basically the service level agreements are getting stringent, and any downtime is very expensive, and because of that data centers are investing heavily on hardware, software, and other infrastructure components, as well as mechanisms to monitor the incoming data and monitor the health of the data center as a whole, and putting in place predictive mechanisms to predict any impending outage or any such sort. So we'll go through that. So increasing amounts of data is produced from a variety of devices, and they are stored and processed in various different ways. And the higher workloads on the data, it all puts higher amounts of workload on the data center, as I said. So what are some of the workloads characteristics? So we have service workloads, which are basically online workloads where somebody does a web search or a web serving or a media streaming or data serving. And there can be other workloads like the data analysis workloads, which are basically offline. So the difference between the two service, the two workloads, the online and offline, is the response time is kind of critical in the service workloads, which are the online workloads. So when you do a query or when you do a web search, the response you are expecting is quite fast. And again, in the case of media streaming, you don't really want any stall of the media or of that sort. So the offline workloads are kind of the maybe big data analytics, or you are doing a lot of analytics on the backend database, and then that could be even batch workloads and things like that. So these are the two different types of workloads that we are having in the data centers. So why machine intelligence in the data center networks? We see that demands on the data center network infrastructure is increasing, and evolving traffic scenarios. So earlier, we had a very less number of traffic scenarios where you have got the north-south traffic, and now we are having multiple levels of traffic like north-south, east-west, and API traffic, and then the real-time traffic, and so on and so forth. So the uptime and the service level agreements are going to be very high. So to meet all these things, some kind of intelligence mechanism is needed throughout the data center. So if you look at the data center components, there are three basic components: the servers, the networking switches, routers, and load balancers, and the storage arrays. So these kinds of machine intelligence needs to be deployed in all the three aspects of the data center, all the three components of the data center network. So and again, the amount of intelligence, or the amount of intelligence that we can gather, it depends on the quality of data that we have. So when we have the monitoring systems and the data collection systems making use of the telemetry applications and other standard mechanisms like collecting the logs, and then the other mechanisms like the packet collectors, packet tracers, and so on and so forth, also the environmental sensors and other things. So how this machine intelligence will make use of all those data collected, and then provide some kind of a predictive mechanism so that we can proactively avoid the service outages. That's what we're going to see. Before that, we can see these data center characteristics. So it's basically growth in scale and complexity, and problems could occur, because there may be addition and removal of system components, and the changing execution environments and changing workloads, and updates and upgrades to the software and firmware and things like that. So a newer firmware in the switch can be there, but a older firmware in the server software or in the in the storage array could be there. So at any point in time when a new upgrade or new update comes, so it has to be applied, and then when it applies, it should be seamless. So the dynamics goes like this: the software upgrades are very common, and these protocols also evolve. So new protocols come in, and then people want to deploy the protocols and make use of the protocols for various new services and applications. So new application services are coming up, and traffic fluctuations and routing anomalies, misconfigurations, and the network migrations and convergence and customer changes, upgrades, surveys, and things like that. All these things are playing major part in the network dynamics as such. So a typical statistics says that there are about 400 plus network failures that occur each year in data centers. So they lead to extensive losses due to lack of responsiveness or availability. So the predictive intelligence that could lead to reduced downtime and maximum efficiency. So the key components here is the prediction part, which is basically prediction of an outage in advance, and proactively mitigate the ill effects of the anomalous behavior. So as a result, of this outage, everything is kind of seen mostly in the application side. So there are the servers, and then there are some applications running on the server, and the server operating system is running, and then you have networking connectivity all the way to the networking switch, and there are cables, and there are optics, and then this switches running a number of protocols, and then the storage array which also taking part in the entire operation. So whatever happens inside the data center network, which is classified as an outage, could be there anywhere in the whole ecosystem. But whenever anything happens, it basically is seen mostly in the application space. So the server applications, they experience either connectivity disruptions, or you see the latency issues and throughput issues, and or the application completely fails. Some backup application need to run. So for want of any of these failures, the application simply fails. So we also have the requirements of IOPS and latency requirements for different applications and for different services. So all these things need to be addressed in the case of the data center as such. So what could be the root cause of these outages? As I said previously, it could be this server host or the network interface cards or the HBA, the host bus adapter in the fiber channel world, and the CNA, the converged network adapter, or router, switch, load balancer, firewall, or storage controller, or a disk array, or the cable, optics, and media. So the other part is the system failure or the protocol software failure. And third thing is this application failure. So to avoid all these things, we are talking about this machine intelligence framework. So this framework consists of what? The framework consists of this basically a data architecture, because we are collecting data from a variety of devices, be it a server, be it a switch or a router or a load balancer, or even a storage array. So we have a bunch of information, and then to store all the data and efficiently process to gain some intelligence from that, we need a data architecture. So the data architecture could be should be capable of storing a large amount of data. So basically historic data as well as the real-time data, and some of this data will also be archived for further retrieval and processing offline. And we need to have mechanisms to blend and ingest a variety of structured, semi-structured, and unstructured data. So for example, if we get the port counters and all these things via the telemetry, so they are basically unstructured, and then we get a stream of data, and then we have some of the things are some system logs, and then this protocol logs and things like that. They have a specific format, and so they're kind of structured. And with all these data, we need to discover patterns and hidden correlations on that. So that is one of the main goals of this machine intelligence framework, and also detect anomalous behavior and predict failure, and root cause the anomalous behavior, and suggest decision options and their implications. So in all these cases, the main goal is to kind of arrive at an architecture and also arrive at some of the mechanisms for the machine intelligence to take place using various learning algorithms, using various correlative analytic methods, and so forth. So typically, what are the sources of data that we have? So logs, and many of these systems are designed to generate alarms, traps, and then traffic statistics, counters, and in many cases in servers and networking, we have this packet traces, and then IPC messages, and network telemetry is also very common these days, and then system config files and so forth. So these are the data that we have, and the data characteristics are some of these things are kind of textual, and some of the things are numerical, some of these things are both textual and numerical. So with all these data, what is the framework for arriving at a analytic model? So basically, many of these data will be having not all data will be captured, or some of the counters will be missing, or there will be some missing values, or the data gathered will be some of the sensors may not work perfectly well, and so that you will have a value which is kind of out of the range and things like that. So basically, the first step is to do the data cleansing, and after you do the data cleansing, there is this huge data, and with all the data, the dimension becomes so high that many of the desired algorithms will not work because the dimensionality is too high, or the storage capacity that you have for the infrastructure to process that is limited. So you select the features, or you reduce your feature set to a little lower, so that you pick only the features that are very relevant in the prediction, and or the specific feature which contribute more to the prediction. So, and then you represent the features, and then you apply some learning. I mean, you act upon this data with some learning algorithm, and with that learning algorithm you arrive at this analytic model. So some of the data that we gather and the specific feature engineering methods that we use, they result in an optimal set of features where every feature will be kind of distinctly bringing in one set of bringing in one characteristic feature of the data that kind of distinguishes between anomalous behavior and a normal behavior. And then the data determines the characteristic and the nature of the machine learning technique or the machine intelligence technique that we use. So the techniques used for this analysis intelligence that depends on the nature of data. And say, for example, right, if you have data that very well, I mean the data is mostly, if you have some 100 fields or 100 features of the data, and out of the 100, if around 40-50 are highly correlated, so that data may not be of that useful. So what you do is, like, you take specific data sets, and again the same techniques that will work on one type of data will not work on a different type of data. So as the data characteristics need to be taken into account when applying this machine intelligence techniques. So there are data which are kind of time series data. So in this time series data, you collect data over a period of time and at constant intervals of time. So you have the seasonality and trends and things like that. And what you actually do is, like, when you take the data, it will be raw data. When you do the cleansing and things like that, you kind of do some processing on the data to remove the seasonal variations from the data. And there are some use cases which are specific use cases in the context of data center. We are going to see is this the network traffic prediction. So which is basically a regression, meaning it's basically computed on the values of numerical fields. And say there are multiple sessions that are running from say a database to a server to a database, or some protocol sessions are running, and the sessions could drop at specific points in time. So the session drop prediction is basically a classification problem, whether there's going to be a drop or not. And then the system failure prediction using these logs, that's also a classification problem. Like, the system is trending towards a place where you are going to have either the servers failing, or you have the network switch failing, or you're going to have an extreme amount of traffic at the storage device. And then there could be things like reservation conflicts and other things that can happen in a storage array. So let's go into the details of each of these use case. So basically, network traffic prediction is basically a time series based prediction. So more than one time dependent variable can be there. So the variable depends not only on its past value, but also have some dependency on other variables. So it just fits into a multivariate time series analysis problem. So what are these specific characteristics of the time series? So there is a trend over time, that is a gradual increase or decrease of activity over time. and there could be seasonal trends or cycles. For example, traffic increases in the morning hours and peaks in the afternoon and declines at late night. And there could be seasonal variability. For example, application request fluctuates widely minute by minute during the peak hours of maybe 4 p.m. to 8 p.m. But at 1 a.m. the application requests hardly vary at all. So this 4 to 8 is the prime time, and then it depends on how many people go on, and then if kind of there's an activity going on or some sports activity going on, and then people are always streaming the data and from there and things like that. That time it could peak. But at 1 a.m. The application requests hardly vary at all, so it reaches a steady state. So the next thing is that anomaly prediction. So protocols like OSPF, BGP, and BFD, they establish neighborship sessions as part of their state machines. So the session drops could be seen due to loss of hello packets. So this will result in outage in the network. So system and network parameters are available with the monitoring. So now the question is, can the outage be predicted with all these? Yes. So with the past experience, we have all these predictor variables through which an anomaly prediction can be modeled as a classification problem. So CPU utilization and memory usage, the over temperature alarm, and kernel queue drops and hardware queue drops, and interface packet errors and packet discards. All these data we used to collect in some form or the other, and then we ingested into the data architecture. And with all these things, the drop can be predicted. So what are some of the methods that we used for predicting this kind of drops? It's basically logistic regression, support vector machine, and naive Bayes based probabilistic classification, and decision trees and booster trees, random forest, and neural networks. So each and every one of them have their own characteristics, but in this specific case, we can use logistic regression and SVM for in our experience, these logistic regression and SVM, they are giving a kind of better prediction of the session drops. So next thing is the system failure prediction using log analytics. So logs have a lot of data. It's basically a textual data. So from this text, we gather some specific, we run it through some algorithms to gain some specific feature set. That feature set could be either it could be dependent on the server based logs, or it could be based on the network device based logs, or it could be the storage device based logs. So where you have logged some specific instances, or we have some specific symptoms that you have incorporated in the log, that okay, this symptom has been seen, X symptom has been seen, or Y symptom has been seen, and things like that. So when you take the log and then you pre-process the log, and then you feed it to kind of the recurrent neural networks, which are basically used for the text analytics in almost every context. So what this recurrent neural networks capture is basically they capture the implicit system behavior, and you have the log, and then you have say, okay, this is a log which is kind of okay type of a log, and this is a log where you find some anomaly in say this protocol failure, or you have this where you end up depleting all your queues in the network and things like that. So when you feed that all this, so the recurrent neural networks learn all these behaviors inside their network. And so since the similarity is captured from the log entries, so when you feed in a new log, then this new log will kind of tell that okay, the neural network will tell that okay, this is a kind of a pattern that is trending towards say a protocol failure, or basically a failure that will be there in the protocol packets drop, or it could be there in the buffer depletion. So how do you actually have you train the network using these recurrent neural networks? Basically there's an input layer and there can be multiple hidden layers. So this is known as a deep neural network if the number of hidden layers is more than one. So basically the output layer is basically a class or target. So these specific words, the specific logs are analyzed, pre-processed, and then are sent as the input layer, where the specific keywords derived from the logs are given as input to the input layer. And with the neural networks training by itself, then the output layer will give you the class, whether it is the system log corresponds to any normal behavior or an abnormal behavior. And the system failure prediction finds this kind of neural network finds the semantic relationship between the words. It consists of a hidden layer acting as a memory that stores the internal state of the log data. Then the training data is used to recognize the failure within the system. As new data arrived, the memory is updated and decisions are made according to the current and previous input. So to overall, to sum it up, is basically an architecture like this, where you have the data that you get. You basically cleaned the data and then you extracted the feature and you represented the feature, and there you get you pass it through the learning algorithm and you have a model. So when the new data comes in, and then it also undergoes the feature extraction and the feature representation phase, and then it's with the help of the model, the anomalous pattern is detected. So once the anomalous pattern is detected, there are a couple of things that the user can do. It's based on the human intelligence, where the system engineers and the service engineers, they go through these logs over and over and over again, and they say that, okay, hey, in this case, we are trending towards a pattern where we'll have a lot of data, and we see some head of line blocking, and there is necessity to kind of deploy, or we need to change, or we need to dynamically change the port characteristics, and we need to kind of program the underlying ASIC in a different way. So that could be one of the mechanism that could proactively avert the anomalous condition. And then let's go to the next one. This, what are the hardware and software features, or what are the hardware and softwares used for these kinds of machine intelligence mechanisms? So basically, traditionally, when they started with these kinds of analytic methods, it used to be only kind of charts and all these visuals and patterns that is displayed on the graphs and things like that. So CPU itself on a server would be sufficient. Then when it came to kind of training models and take the huge amount of data, the CPU kind of cannot cope up with all these things. So the GPUs they came into picture, and in today's context, GPUs are one of the widely used hardware for training as such. In some cases, the FPGAs are also used for kind of these kinds of training and inferencing basically, and even the tensors are coming now. Tensor processing units are also coming now. This is proprietary of Google. And the software wise, there are open source packages that are available for either from all the way up from the data cleaning and the data wrangling and kind of applying the machine learning algorithms and all these things, or people can go ahead and then have their own custom software for their own needs, because some of these data that is that the users know better, and they know how to make the data, how to make best use of the data. And that's pretty much everything that I have to cover. So, any questions? Yeah. So one typical case study was that during this holiday season, right? So everyone goes online and then kind of order stuff, and then they wanted the order to be processed, and so the everything goes to the data center, and then people order multiple things, and then all these things are kind of increasing the load on the servers. So it's basically, as I said, it's a kind of a specific multivariate regression problem. So with those regression models basically, and accounting for the seasonal variations, I mean the daily variations or the nightly and daily variations, we were able to kind of predict what exactly could be the system load in terms of the number of packets flowing through the network and the traffic characteristics. So that we were able to predict. That was one of the use cases. Yeah.
And also you are getting all the logs from different things like alerts,
right?
From power systems. So they're all in different formats. Like one is a text format, one is a numerical format, another one is like maybe something else. And mostly most of them are time series related. Some of them may not be time series.
That's correct.
So when you are combining those two, so how do you normalize it, or how do you make it?
Yeah, all the numerical values are normalized, and so the key here is that there is no single one model that will do all sorts of things. So it is basically a combination of all models. It's a combination of multiple models that come into picture here. So the log data, we have a separate kind of a machine to process all these things. There's kind of a, I shouldn't say the machine, and there's a kind of a separate processing unit that does all these things. So there are when the data comes, we identify, okay, which are the things, which are the data that will go into one engine, which are the data pieces that will go into another engine. So for example, text goes into one engine, and all the numerical goes to another engine. And even in the numerical, not all data are kind of fall within the same range. So as you said, we need to do a lot of normalization onto that. And basically, it's a combination of multiple models, combination of multiple engines, and a combination of different processing techniques to arrive at this. You had a question?
So how does the model differentiate between an activity that is helping to resolve the outage? Because during the activity, the outage is going to be for longer periods of time. So does the model have some way to differentiate it, or?
No, the objective of this model is to find out whether the system is behaving in a normal way or it's an anomalous way.
Yeah, but so I have an outage.
Right.
So the current data indicates that I have a 1 hour outage, but out of that 1 hour, most of the time is for fixing it, might be at a physical level or something.
Right.
So because you are analyzing on the existing data, the 1 hour might not be necessarily reflecting the error there.
Yeah, so this specific anomalous detection is like, okay, it is based on the objective is to find out the outage much in advance. So what we have is we have the historic data. Okay, these are the things that has happened, and at that particular time, we had an outage where some protocol failed. So that data we capture, and that data we feed it in. So mostly the objective is that to predict this outage much in advance. So in this case, whatever you are saying is a specific case where the outage happened. So that the system will say that, okay, there is some outage, but the specific nature of the outage that we need to really feed into the system. that intelligence is not there yet. So again, in this case, the challenges that we face are like, okay, we have only n number of outage conditions that we have, but if you see that over a period of time, there will be maybe 80-90 hours of the good data and only about 10 hours of this bad data or the outage data. So when you always when you have such a situation, the thing is that you cannot just use that data set to kind of predict. So you need to kind of enhance the data set with something like SMOT or something like that, because you know SMOT, right? The synthetic minority boosting algorithm, like in the sense the data set which is bad, or the outage data set is only 10%. You add some synthetic data to that with more outage cases, so that this also comes to maybe 40% or something like that. Then you run the algorithm, then the algorithm will work better. So that's the way it works. Any other questions? Yeah.
So, in terms of predicting hardware failures, do these models also help on finding the root cause of failures over time? Can it correlate like different failures?
Yes, to some extent. Yeah, to some extent. So see, one of the major components on all these devices is that the solid state devices and things like that, and they have some maximum write capacity and things like that. So you have this, and then with sensors you can always read that. So some rogue application is running, and then it's just pumping data onto this, and then you see, and then you see the trend, you see the pattern, and then you see that okay, this is if you extrapolate it, if you kind of do regression analysis on this, it can be seen that this is going to kind of hit the maximum writes on that. So that can be predicted. I don't know if I answered your question. This is one of the use cases. Okay, thank you very much.